And welcome. My name is Scott Newbold. I'm a member of the biology faculty here at the college, and for many years have been fortunate enough to help coordinate and organize our lecture series with help from folks in our Museum of Discovery, like Dave, who's here, and others. And it's my pleasure tonight to introduce Bob McDowell, who's here maybe for his 5th or 6th lecture over the years. The topics keep getting better is all I can say. So this is exciting. Our next lecture, this is the last one for this season, for this semester. Our next will be in February, and I believe it's a local falconer talking about his research program in mostly Texas on Aplomado falcons. Brian Munch is the person from the Peregrine Fund. Mid-February maybe. So many of you know Bob and might be familiar with some of his work in research and development related to automotive catalysts. He was part of the team that brought the first commercial 3-way catalyst from concept into production and has manufactured emission control catalyst on 4 continents. He currently advises a diverse set of clients working in R&D and prototyping areas, including lithium-ion batteries, biofuels, precious metal recycling, and emission control catalysts. What you might not know but might suspect is that Bob has many irons in the fire all the time. In addition to his catalyst consulting work, he had a recent project where he was trying to work on ways to isolate pure graphene, and graphene's an atomic scale lattice made of carbon atoms. Had to look that up. It's not. Graphene has many uncommon properties. It's the strongest material ever tested, conducts heat and electricity efficiently, and is nearly transparent. So that's one of the recent things Bob's been working on. There are others. Bob has also become a semi-regular lecturer in some of our life science courses, and he was involved with the installation of several new exhibits around campus alongside Dave Nicol-Larsen that showcase impressive fossil specimens and their associated stories from our Museum of Discovery collection. Tonight, he'll help us understand the various planet-scale modifications known as geoengineering strategies that collectively seek to mitigate climate change effects such as warming. Bob, take it away. Thanks for being here.
Appreciate Scott asked me to come up with the topic because it's always something that's going to be a little bit different, a little bit interesting. So appreciate the topic selection. Tonight, I wanted to talk about geoengineering and climate control. As Scott mentioned, I spent a lot of time working with anti-pollution and catalysts. When the first catalytic converter started out in the 70s, we were looking at 3 pollutants: hydrocarbon, carbon monoxide, and nitrogen oxides, HC, CO, and NOx. So that was the pollution we were trying to control. We knew carbon dioxide came out, but we knew there was nothing we could do about it. And so far, after 50 years, it's still not really able to be controlled on a vehicle-by-vehicle basis. So I am interested in this, and this is going to be pretty much how it works, what are the ideas, and then how do they work. But I hopefully will have time at the end to talk about some of the other implications, why they're not being initiated now, and some of the moral, ethical, legal, and societal implications of the projects as well.
Got stuck again, so if we escape, and that started again. That's good. That's right.
There we go.
Yeah. Okay.
So the outline for tonight: who, what, why, where, when, and how questions. We'll talk about solar radiation management. You might see that SRM, carbon dioxide reduction, CDR. These are the techniques for each of them, and then you'll be surprised, but the conclusion is we got to do something now. Oops. So why do I think geoengineering is necessary? It's the growth in the population from 1950. Today, it's gone up 4 times. It'll go up 5 times in less than 100 years. That's unsustainable. What a friend of mine did about 30 years ago for one of his thesis works was did a direct correlation between the use of electricity and population. And as you get into the middle class and the upper middle class and the upper classes, energy, or at least electricity usages, go way up. So if you'll notice down here, we've got Africa, we've got Asia, we've got Africa, and then everybody else. The 2 continents, Asia and Africa, have the majority of poor people. So if all of a sudden, all the poor people in Asia and Africa started living a middle-class life, we'd run out of everything. But we'd also fill the skies and the ocean with CO2. And we're going to be talking about CO2, carbon dioxide. But there is another greenhouse gas that's even more vicious, methane. And right now, methane accounts for about 15% of the global warming potential. I'll only be talking about carbon dioxide tonight, but always keep in the back of your mind, what about methane? What about methane? This is the data that's been collected since 1958. A guy by the name of Charles Keeling started measuring the CO2 in the atmosphere. And the cleanest atmosphere he could find at the time was on top of a volcano in Hawaii. So he started measuring, and he measured just about 300 parts per million. Today, we're running 421 or thereabouts. Again, just CO2. If you throw the methane in on top, it bumps it way up into the high 400s. And again, they changed the site. They went to another volcano. I'm not sure if that was because they wanted to or because they had to. If you look at that, remember that curve, that's where we were in 58. That's where we are today. If you come back about 800 millennia, 800,000 years ago, you look across, CO2 level has only been up to 300 once in the last almost million years. They get this data from ice cores trapped in the glaciers up in Greenland. So why is geoengineering necessary? Well, number one, we've got a lot of CO2 in the atmosphere. We also have it in the ocean, which wasn't really expected until about 10 years ago. Nobody seemed to bother about that. 420 parts per million doesn't seem like a lot. That's 0.042%, right? I mean, if you got change for $1 and you got 99.94 cents back, yeah, you wouldn't complain too much, right? It comes out to be 1.6 trillion tons of carbon dioxide that's been accumulated since the start of the Industrial Revolution. So 420 part per million is a lot. Hopefully you can see this. It's a little bit busy. Here's the part per million level that we talked about before, and of course we're way up here now. But if you look at some of these peaks, especially this peak and this peak, at this top graph, this is a rise in sea level. And surprisingly, they match up almost exactly. Every time the CO2 peaks go up, the ocean levels go up. And on these two, this particular 400,000 years ago and 125,000 years ago, the geologists have found evidence that there was a crash. There was a very, very quick ice melting event. So probably had some nasty tidal impacts. So if you were Homo habilis or a Neanderthal man back in those days and you had your little village sitting on the shore somewhere, you were probably wiped out. We are going to have the same problem. This is a little bit more modern curve, 1992. This is sea level rise. Just like the Keeling curve, we get a lot of variability in it, and it's seasonal. As the Northern Hemisphere Spring comes, there's a release of carbon dioxide because all the dead matter over the winter starts to decompose in the spring, the CO2 level goes up. Come the autumn, all the trees have got fully grown with the leaves and all the crops have grown, so the CO2 level goes down. We see a similar pattern with the sea levels. So again, the ocean and the natural systems are pretty well tied together. So why is geoengineering necessary? Well, we've got the atmospheric heat, the climate warming. Not only is it warming, we're getting more variability, more flooding, more drought, more cold spells, more hot spells. All of that affects the food, really affects the biodiversity, which we don't pay a lot of attention to, but with the warming, a lot of the plant and animal life is migrating to higher altitudes. We're seeing species moving up in altitude. And we're also seeing species move up north. Some are good or some are bad. You've got the dengue fever now coming into places like England, Texas, and Florida, where it was always in the tropics. Now we're getting a lot of the tropical diseases, bacteria, mosquitoes, moving up further and further north as the climate warms. Huge ocean effects, not just the melting of the ice and the flooding of the ocean's rise in sea level, but the acidification of the ocean. All this is impacting all the fish, all the phytoplankton and all the krill that the whales feed on, that sort of thing. We've got about 600 million people living within 10 meters of the ocean, within 10 meters altitude of the ocean. If sea level rises continues, and with 100 years, they're going to have their feet wet. And before that happens, they're going to be a lot more susceptible to hurricane storms, tidal surges, that sort of thing. New York City is about 4 foot above sea level. Subways aren't going to be a good place to be, before too much longer, not just for the crime, but you're going to be wet. And about 1 billion, mostly poor people, will be living in coastal areas in about 25 years, 27 years from now. And where are they going to go when they can't live where they live now? One of the big reasons for the decline and fall of the Roman Empire was a lot of climate refugees or refugees from Central Asia being pushed into the European side of things by the Huns. We're going to have potentially 1 billion people looking for a place to stay. Are we going to be able to find places for them? What is geoengineering? It's the deliberate large-scale intervention in Earth's natural systems. We've already done, by accident, we've really intervened already. 2 categories, the solar radiation management that I mentioned, and then the carbon dioxide reduction. The solar radiation management has nothing to do with carbon dioxide. Basically, it's putting up an umbrella, a parasol. So if you're hot, you put up a parasol, you block the sunlight, but it doesn't change the air you breathe. So if we initiate solar radiation management and don't do anything else, the CO2 levels are going to continue to rise. Carbon dioxide reduction actually means pulling some of that carbon dioxide that we throw into the atmosphere and the ocean every year, pulling that out. And ideally, we want to pull out some of the legacy carbon dioxide that we put in over the last 300 years. Let me get you a better picture. Okay. I like simple sketches. I'll get you pictures later, but this helps me. Solar radiation management is this diagonal line here. So far away from the Earth, you put up a sunshade in space. About 60 or 80,000 feet above the Earth, we can put in stratospheric aerosols. About 5,000 feet or lower, we can put in clouds that we generate from salt water from the ocean. And then on the surface, we can increase the albedo. The albedo is basically a Latin word for white. So instead of having green crops, blue ocean, if you can make everything white, it'll reflect more light, cool things down. The surface part of the equation here, most of this is the carbon dioxide reduction side of things, all these techniques. We can capture carbon dioxide from the air send it underground. We can grow a lot of crops, turn them into biochar, dig them into the soil. We can plant a lot of trees and don't burn the trees and reduce carbon dioxide that way. And we can put things into the ocean that'll help the ocean absorb carbon dioxide even more than it is already. And we can push fresh water down into the ocean, stir it up a bit, because the deep water of the ocean has capacity to store more carbon dioxide. Okay, so this is just the solar radiation side of things, the umbrella. If you put mirrors or a big mirror up in space, it'll shade the Earth, make it cooler. The whiz kids at MIT figured if you could cut the incoming solar radiation by 1.7%, we could stop the temperature increase at the 1.5 degree level that we're almost at now. So we don't need to change things much in terms of a percent. The second thing I mentioned was the stratospheric aerosols. This idea is you basically tether a balloon above the flight path of the airplanes, inject sulfur dioxide particles in the stratosphere. Stratosphere and the normal atmosphere tend not to mix a whole lot. And so this would be a relatively long-lasting thing. It would need to be done continuously. We can thin out the cirrus clouds a little bit lower. We can thin them out because they tend to trap the heat more. So, and then at essentially sea level or slightly above, we can make more clouds from salt water. And this neat one here, we don't talk too much about, it's a relatively new idea, is putting micro bubbles into the ocean. Basically what they found was that if you can generate a lot of small bubbles, the bubbles will last a long time. They gradually get bigger and bigger and bigger as they coalesce in each other, just like the foam on your beer at night, right? So the smaller they are, the longer they last. And if you put micro bubbles or put a head on the ocean, white is a lot more reflective than the blue ocean, so you'll reflect more of the energy. Oh, I did have a bigger picture, sorry. Okay, now we're back to solar radiation. This is the parasol. Back in the early 1900s, a guy came up with the idea of putting a mirror into space. This is the sun, this is the Earth. And then in around, I think in the 30s or so, this Italian guy by the name of Lagrange did all these calculations on the three-body orbiting astrophysics stuff. And he came up with these 5 points, Lagrange 1, Lagrange 2, 3, 4, and 5. What you can do is you can put a small satellite here, and based on the solar mechanics, they'll stay there forever. And we're already using the Lagrange 2 point for the James Webb Space Telescope. It's about 1 million miles from Earth. You put something there, and it'll stay in position for a long time. The reason we put the telescope there was it blocks the sunlight from this telescope, and the telescope needs super cold temperatures because it uses infrared radiation from the exoplanets and stars from billions of years away. So in this case, the Earth is the sunshade for the telescope. Guy by the name of Early, I think it was, at the Lawrence Livermore Labs came up with this idea of putting a telescope, putting a mirror 1 million miles in front of the Earth. And as the Earth rotates around the sun, this rotates around the same way like the spokes of a wheel, and it will always shade the Earth. It's a little impractical. The mirror would have to be about 1,000 miles in diameter, right? So even Elon Musk doesn't build a spaceship that big. What we could do instead is kind of like the sulfur aerosol idea. You put a dust field out there 1 million miles in front of the Earth. And where do you get the dust? Well, one idea is you just move an asteroid there. We've already hit an asteroid and moved it with a impact rocket about a year ago. So it can be done. And what they do here then is they have it basically a miner or an auger and a catapult. So you grind the asteroid up, inject the dust, and the dust forms this shield or this shade 1,000,000 miles in front of the Earth. Blocking the sunlight cools the Earth down. There are a couple ideas along the same lines. One is to do that on the moon, so it would be closer to Earth, and all that moon dust that they inject would be the parasol, would be the umbrella. But it would have to be a lot more of it because it's closer to the Earth. A lot of it would come down. We wouldn't notice it if the dust was, foot in diameter or so, but if they started getting in big chunks, we might see some neat meteorites. Another analog or spin-off from that idea is if we're going to put satellites up, if we're going to spend a lot of money putting up rockets, why not put up big solar panels, generate electricity, microwave the electricity to Earth? That way, you can shut down some of the 100 or 200 new coal plants that are being put up in China, cut out their CO2 emissions, and we would have that essentially CO2-free energy to use. Now we drop down from outer space into the stratosphere. Some of you are old enough to remember 1991, Mount Pinatubo went off in the Philippines. And then it injected a lot of sulfur dioxide particles into the stratosphere. And so the Earth actually cooled down by 1.5 degrees or so for about 1.5 years, because that sulfur, once it got up into the stratosphere, basically circled the Earth and gave us about 1% shade. Eventually, the particles do come down to Earth, but they gave the guys an idea. Now you've got a stratospheric balloon tethered to ships if you want to get them out of the way, if you don't want them on land. And it's 60,000 to 80,000 feet up, so above where the airplanes fly. You can still go your trips to Bahamas and places like that and not worry about hitting balloons. Kind of neat thing here is, I don't know if you can see this, this is basically an inset for the tether cable. Getting a rope 60,000 feet, 80,000 feet plus the angle, so maybe 100,000 foot long rope that's strong enough. We can actually do that now with these hollow carbon fibers. And our friends up at 10 miles up the road at Ramaco are working on turning our Donner River Basin coal into graphite, into carbon fibers. So this may be something that will help out Sheridan as well. This may look familiar to some folks that like to go skiing, basically snowmaking machines, right? Only instead of making snow, they're pulling up seawater. This is off the Great Barrier Reef in Australia. So basically you pull up seawater, you pump it out, you mist it. Some of the water evaporates and you're left with tiny salt crystals. And the salt crystals act as a nucleation site for the humidity around that crystal. So that always tends to have water surrounding the salt. And it's relatively low-hanging cloud, but it is a cloud and it will shade the area. Now, they did this for about 3 weeks, I think. They ran these things, and it did actually drop the water temperature underneath the man-made cloud, and was a pretty convincing argument for the folks on the Great Barrier Reef, where the heat was bleaching the corals and potentially destroying the biggest reef we have in the world. This last one is the simplest one for me, working on the albedo, making everything white, right? When we had snowball Earth, there was the sun's radiation coming in, most of it was reflected, the heat stayed fairly small amount in the Earth's environment. The same amount of energy comes in when we're half and half, less goes out, more stays. And if we lose the ice caps, the polar ice caps in Greenland and the glaciers, basically most of the energy coming in is going to stay in. And that's what's causing the greenhouse effect. So we've got nice white ice in Antarctica and a lot of it up in the poles, a lot of it in the tundra. Trouble is, a lot of it's not white anymore. You get wildfires putting out particles of dust. You've got diesel engines, you've got industrial particulate emissions. That gets in the atmosphere, floats around the Earth. makes the white ice dark and it melts a lot faster. The other thing, good and bad, there's always a balance, right? If you want to make the tundra and the northern arboreal forest a lot more reflective, I'll just cut down all the trees because the trees are green. So make it all white and you'll help cool the earth. Unfortunately, they won't pull carbon dioxide out of the air because it's not going to be there anymore. So that was solar radiation management. Jump up if you have any questions. I don't want to be going too fast, but we'll have time at the end for questions too. Carbon dioxide reduction. These are all the methods that I'll talk about we can use for pulling carbon dioxide out. And it's not just, remember, it's not just out of the air, it's also out of the ocean. The ocean actually stores more carbon dioxide than the air does. So the first one is the simplest, afforestation, plant crops, plant trees. Europe has more trees now than it did in the last 300 years. Is that good? Well, we got room for more trees. There's a lot of places we could put more trees. Unfortunately, if we filled up the earth twice with trees, it wouldn't take out all the CO2 we already dumped into the atmosphere, into the ocean environment. So it's a good start, but it's not going to be the answer. What if you took those trees you're growing and partially burned them, turned them into charcoal? You'd admit that they would pull the CO2 out of the air. You would get CO2 from partially burning it, so you'd have to capture that and sequester it. But then you'd be left with charcoal. And charcoal, amazingly enough, is great for the soil. About 800 years ago, there were tribes in the Amazon that had the old slash and burn technique. They would clear a patch of jungle, plant, ground. And after about a year or two, they couldn't grow anything. The soil was so rotten there, a lot of clay and constantly being leached by the rains. They put charcoal in with their soil, and 800 years later, you can still see the difference between where they put it in and where it's not. So they were a lot smarter than we are. It does all these good things. It increases the moisture retention. It's very porous, and so the roots can get in and around the, you can get the bacteria, you can get all the microbial activities, and makes the soil a lot more friable. And one of the main things is it acts like a sponge and holds water, so makes plants a lot more drought tolerant. This is what most people now call BECCS, so bioenergy, carbon capture, and sequestration. So basically what the idea is here, you grow trees, you chop them up, you gasify them, or you ferment them, or you partially burn them. You turn the carbon dioxide that comes off into CO2, and then you bury that in the ground. What you make is fuel, either ethanol, diesel fuel, they call SAF, sustainable aircraft fuel, they call it now. So you burn the fuel, and that turns back into carbon dioxide, and you start to cycle again. So every time you cycle, you're pulling out a certain percentage of the CO2 and you're sequestering it. Kind of a halfway house. It's not really a great idea, I don't think. But you may see the oil companies pushing that pretty hard soon. And this one is a real neat idea too. They call it DAC, direct air capture. Basically, you pull air through a filter, you trap the carbon dioxide particles, then you take the carbon dioxide particles that you've trapped off of the filter and sequester it. So this is kind of neat because you can put these plants anywhere, right? Doesn't matter if it's on the top of the volcano in Hawaii or in Iceland where they actually have a demonstration plant going. Could be in the Amazon, could be anywhere because you're just pulling out of the atmosphere. The better bet is the direct exhaust idea where you can pull it right out of the exhaust stack. Now, they're doing that over at the Dry Fork plant in Gillette, where they've actually put taps into the exhaust stack, and you can pull out samples and do your test work there. And there is one commercial plant that's doing it. There used to be two. There's one in Texas that started up and didn't last too long. And there's one up in Canada near the Montana border in Saskatchewan, where they are pulling out about 1 million tons of CO2 out of the exhaust. Why is the exhaust better than the direct air capture? It comes back to that parts per million idea again. Parts per million of CO2 in the air, we said was 420-ish. Part per million in the exhaust would be like 150,000, about 15%. So if you're trying to capture something, somebody spread out dollar bills all over the place, would you rather capture where the big pile is, or would you rather capture it if it was spread out over the whole campus? Well, go for the pile first, right? And that would be the direct exhaust. How does it work? Oh, here's what a theoretical plant would look like. The one in Iceland is pumping the carbon dioxide down right next to the geothermal plant that's giving it the electricity. It hits the hot, wet rocks down there and turns into a carbonate, a rock. So they figured it would take about 10 years. They actually drilled down and took some samples after 2 years, and it's all solidified after only 2 years. Now, see if I can make this work. This is a company from Switzerland.
The air is drawn into a collector with a fan, and CO2 is captured on the surface of a highly selective filter material that sits inside the collector. Next, once the filter material is full of CO2, the collector closes and is heated to around 100 degrees Celsius. Using the carb fix method, the captured CO2 is then mixed with water and pumped deep underground, where it mineralizes and can be stored permanently for thousands of years.
That's the idea. Now, that filter that you saw there, it's another neat thing. I don't know if you're familiar with scrubber systems, but if you've got a nasty acid exhaust or something, you blow that exhaust through a curtain of water. Basically, the water dilutes, it catches the acid, and you can get that and neutralize it and dilute it. For CO2, you can use a curtain of what's called an amine. The CO2 likes to go into the amine solution. Basically, it's you pull the air through this curtain, wet curtain, and the carbon dioxide goes into the amine. And then you heat the amine up and it dries off the carbon dioxide to catch it. Well, the idea of the filter is much, much better. Now you're not heating up, spending a lot of energy heating up a pool of liquid, whether water or amine or whatever else it is. Here you're just heating up a filter, a small filter. And one of the things that the guys at Ramaco are doing again is working on the turning the coal into a porous carbon, which is very high surface area and attracts the carbon dioxide. So again, something that we hopefully can use the coal for something better than just burning. The other technique here, enhanced weathering. The bighorns probably were taller than the Rockies at one time, but over time, you have carbon dioxide in the air, hitting the rocks, turning into carbonic acid from the CO2 in the rain. And so it starts to erode the rocks. And then you've got the freeze and the thaw, so the massive boulders become smaller rocks, the smaller rocks become sand. If you're doing any chemical dissolution processes, you want to have as much surface area as you can, so sand is the best you can do. You'd rather not have one big rock. You'd like to have spread out very, very high surface area sand. So if you mine limestone and basically cook it, drive off the carbonate from the limestone, capture that, sequester it. Now you can spread lime out onto your fields, good for the fertilization. You can put it on a boat, spread it on the ocean, reduce the acidification of the ocean. They even talk about fertilizing the jungle from the air. Basically, it's counteracting the acid that we have from the carbon dioxide in the air. I was talking about rocks turning into sand. We turn a lot of rocks into sand. Basically, mankind is now moving 24 times more mass than the oceans are moving and the rivers are moving. So we're a bigger effect on the surface of the planet than nature is right now, the erosional patterns in the rivers and the mass wasting. But when we turn things into sand, a lot of the sand we don't use, we get tailings, right? So you got a gold mine in Nevada or a copper mine down in Arizona. You crack the rock, you mine it, you make it nice and small. You pull out your whatever it is you're trying to pull out, the copper or gold or whatever, and you're left with a lot of tailings. The tailings are nice and small, high surface area, and certain plants, and I don't think a bacteria is defined as a plant, but basically growing things can actually use the carbon as a fuel, use the minerals in the tailings to form a nice lacy carbonate material. So we can use nature to help basically get rid of some of that CO2. Going to switch a little bit now from the atmosphere to the ocean. I mentioned the ocean has got a lot more CO2 in it than the atmosphere does. Think about the tremendous surface area. 70-some% of the Earth is ocean. You got wind blowing the waves. So you got a lot of interactions between the air and the ocean, at least at the top of the ocean. One bright spark about 30 years ago saw that this was happening. This is the Sahara Desert. This is the Atlantic Ocean here. About 1,000 miles away from the Sahara, the Canary Islands, Cape Verde Islands. About 1,000 miles away from Africa, there was a big bloom of plant life when the dust storms hit. And they found that was the iron in the dust. Most of the ocean is iron deficient. The iron is a bottleneck for plant growth. If you don't have enough iron, it doesn't matter how much sunlight and how much carbon and how much other stuff you have to grow plants, the plants won't grow. So these dots and these sites here are where some experimentation was done, putting iron sulfate into the ocean. So nutrient addition, they called it, basically iron sulfate. They spread it out, and I forget how big it was. I think it was 50 square miles. And they measured the growth of the phytoplankton and the plant life. This was done down in the Southern Ocean, down near Antarctica, which is a major feeding ground for the whales. And the krill that the whales feed on love to have this kind of stuff, the small. So then you get the krill growing, and then the whales, the fish, right up the food chain. They measured the amount of carbon that they pulled out of the air by estimating how much fish there was, how much growth there was. And by some devious method that I can't understand, they figured about 50% of it hit the ocean, deep ocean floor. So that would be sequestered down there. They think for at least 100 years. It's not going to be thousands or long time, like turning it into rock, but it will pull it out from the atmosphere as well as from the surface layers of the ocean. Real busy chart again. This is that carbon dioxide curve. This is the amount of carbon dioxide in the water. This is just north of Hawaii. This is where they used to measure the carbon dioxide in the air. This is the curve that's concerning to me. Not much of a curve there, but if you go back 30-some years, 40-some years, you see the pH has dropped almost from 8.15 down to 8.05. And again, like the 400 part per million, it sounds like not much. But remember, the pH curve is a logarithmic scale. So for every full pH unit, that's 10 times. So if you drop 1/10 of that, by the tricky math that they use, it figures that the ocean acidity is increased by about 25%. So again, major impacts on animal life and on the ability to take more CO2 out of the air. If you've got acid stomach problems, what do? You take a Tums, right? How do we give the ocean a Tums? I mentioned lime. We can mine the limestone, cook it, capture the CO2. With limestone is calcium carbonate, right? So if you cook it, you wind up with calcium oxide and CO2. So you wind up with CO2 that you can sequester. Then you can load up a boat, drop it in the ocean, You could dose it into a seaside desalinization plant now. There's just getting to be more and more of these around these days. Or you can spread it on the beach and it'll eventually wash into the ocean. All of that's going to raise the pH, make it less acid, and it'll stimulate the ability for the ocean to suck up more CO2 from the air. This is sort of the same idea, but it's kind of neat. It's high science, so I don't understand it. But basically, you take fresh ocean from water from the ocean, and you run it through an electrophoresis cell. So you've got current on this side and current on this side. Think of it of two big plates. And these are tubes running in between those plates. And so when you put a big electrical charge on it, the hydrogen, the plus ions go this way, the negative ions go this way. So if you divide that current coming in, you have basically what's done is an acidified stream. So if you run this underneath a slight vacuum, because it's got a lot of acid now, any of the CO2 that you've created with this electrical field will bubble up and you can capture it and sequester it. Then you recycle the acid over on this side and you pull out the OH groups, and now you've got a base stream. So it's just like adding lime, except you're not adding all the other junk that goes with limestone. This is just purely working on the ocean water that you have. You're not adding anything. So those are the techniques. Those are what we could do. Why haven't we done stuff? Why haven't we done stuff already 20 years ago? Big thing always is cost. Who's going to pay for this? Some of these techniques are a lot more effective than other techniques. There are some safety implications. Do we know what's going to happen to all those sulfur dioxide particles that we might be winding up dropping down to Earth if we're putting in the balloons and shooting out sulfur dioxide? What are the unintended effects? You know, my buddy Donald Rumsfeld's, we got the known knowns and the unknown knowns and the unknown unknowns. What's going to happen? Nobody can tell yet. There are laws on the US books, and I'm sure in other countries, that stop us from doing some of these things. The London Protocol stopped people from investigating that iron fertilization. So there's been no work done on that for 20 years. And what are the ethical implications? If the effectiveness is uneven, right? If we shade the Earth with that giant parasol, it'll mean that the tropics are a little bit colder and the poles are a little bit warmer because of the way that the Earth wobbles and because of the effects. So does your resort down in Mexico go out of business because it's not as sunny as it used to be? Who pays that bill? More importantly, what effects is it going to have on crops? What effect it's going to have on droughts, that sort of rainfall patterns? We don't know some of those things, but we know that there are possible effects. And again, the ethical effects, right? If we don't do anything, we're going to have 1 billion people looking for a new home in 30 years. What do we do with that? All of these things are going to be something that you have to decide on. And like I told the high school kids this morning, a lot of us aren't going to be around to worry about it, but it's their problem for sure. They got to start being a lot more active and talking to the people that can change things. This is a techno-economic evaluation that people in the government always like to see. It's probably because it confuses everybody. Down here is somewhere where you don't want to be. It's not very effective and it's expensive. You want to be somewhere up in this part of the chart where you can afford it, it's relatively cheap, and it's relatively effective. The red dots means they're worried about the safety. Green dot means there's not really any safety implications. So naturally you want to be up in this corner, cheap and effective, and we don't have anything here. Afforestation is relatively cheap. You can get a lot of people planting a lot of trees, but on the effective scale, it's okay. The balloon system with the sulfur dioxide particles, know that it works because we've seen Mount Pinatubo do it. We can be done. All we have to do is mimic nature. It is relatively cheap compared to other things, but cheap being in the trillions of dollars. But we don't know the safety effects. My favorite, the space reflector, pretty expensive, not, could be very effective, but we don't know about the safety. Biochar, relatively expensive because now you've got to harvest the trees or harvest the crops or use the straw or the hay, move it. And again, no idea about the other contaminants that may come through. Painting the parking lots white, painting all the asphalt roads white, kind of expensive, and unfortunately, it doesn't work too well. So these are the choices that people are going to have to make, knowingly or unknowingly. So something to think about. Why haven't we done something? Well, the big thing's cost, and then who's going to do it, who's going to pay for it. Don't have an answer for that, but that's something that we should all be thinking about, because we have changed the earth in our lifetime, for sure. Can we change it partially back again or not? Last but not least, BAU is business as usual, right? If we do nothing, I forget when this graph was made, but it says we're going to hit the 1.5 degree mark. Oh, we already hit it. In the next couple of years, we'll probably go past the 2 degree mark. They were really scared about it, the IPCC convention in 2015. Looks like we'll hit that 2 degree mark early too, within the next 20, 25 years. If we do nothing, business as usual. Solar radiation management's great. We put that aerosol up and we start putting the sulfur dioxide particles in the stratosphere. We can flatline this. We can keep putting out whatever we want on CO2. We have the technical ability to hold the temperature down. Should we do it? Well, sure. We want to keep the temperature down, but we're not stopping the carbon dioxide from going into the atmosphere. Oceans are going to get more acidic. You're not going to have any clams and oysters and pearls because their shells will dissolve. Definitely going to affect rainfall patterns and other things. So what about carbon dioxide reduction? Well, this is going to take a longer time to do, and it is going to have a longer term effect. We've got trillions of tons to work with here that we got to start working on. And the plants, the big plant that's running right now is 1 million tons. So we would only need 1,000 of those plants to just cope with what we're putting out every year. If we do carbon dioxide mitigation, or if we start pulling back in the amount of carbon dioxide that we're flooding the earth with, by itself, if we stop basically polluting in 100 years, we'd see an effect. In 2100, we'd see an effect. So to me, the answer is pretty plain. We've got to do all of the above. We got to stop emitting so much. We got to start thinking about putting some of these techniques into effect. Which ones? All have safety concerns. All are going to cost a hell of a lot of money. Stopping the emissions of the CO2 is the biggest thing we can do right away. That's easy. We just start economizing. And in fact, the US, or North America, and Europe, carbon dioxide emissions have been dropping. Part of that was a pandemic, but still we're cutting back on our carbon dioxide emissions. China and India, unfortunately, have 107 new coal power plants on the books for this year and next year. So about 2 new coal plants a week going in. Right? That's not going to help too much. So my guess is we need to start sucking the CO2 out of the exhaust pipes, out of the stacks of coal plants, anywhere we can on the exhaust side of things where it's more concentrated and got a better chance of cheaply pulling it out. And then the ocean, the TUMS for the ocean, or the electrophoresis system, whereby we can stop the acidification of the ocean. That to me seems the most reasonable prospects. But I'd like to ask, what do you guys think? Because no one person's going to make a decision here. What's going to be the least painful for rich North Americans who run their cars and their air conditionings, take their jet vacations, and ask a Palestinian that question? Now, I don't think he'd worry too much about it. we're the ones that are probably going to be doing it. And should we ask the rest of the world what to do, or should we just go ahead and do it? These are some of those legal, moral, ethical questions that we have to think about and answer eventually. Sooner the better. Thank you. Oh, I didn't put you to sleep.
I know I'm your wife, but I have a question.
Speak up.
I have a question. Do we have the ocean is pretty much owned by everybody. I mean, could we just go out and start dropping in iron filings?
There's no law that says you can't, because there is no, the United Nations says you shouldn't, but they have no power of enforcement. There's a lot of talk about deep sea mining right now. Yes, sir.
When fluorinated fluorocarbons first appeared to be a problem, I think it's the Protocol of Montreal said we're going to stop producing them and stop using them. So if we're going to do a carbon dioxide reduction, shouldn't we stop like carbonated beverages and carbon dioxide fire extinguishers like immediately? Wouldn't that be a step in the right direction?
It sure would be a step. Got to think about the two, though, where they're not really comparable. The chlorofluorocarbon Montreal Convention affected the producers of the carbon dioxide, right? So government just came out and said, you got to stop doing this by X date. And so the companies were on the hot spot. They had to do it. What's the government going to say now? You're going to say Coca-Cola, you can't use CO2 in your sodas anymore?
That's what
Yeah, the people would go nuts.
okay.
Can't have your head on your Guinness? No.
Yeah, well,
That's the political, social, economic situation we're stuck in right now, because the politicians, God love them, I know that they're trying to do their best, but they're not going to touch this with a 10-foot pole. The Biden administration, it's really pushing a lot of environmental issues right now. Just told NOAA, the National Ocean and Aerospace Administration, come up with a plan in 5 years. Not to do anything, just to have a plan, and it's going to take them 5 years. Ridiculous. Yes, sir.
I think it was about 50 years ago, Paul Ehrlich wrote a book called The Population Bomb, and he explained some of the dangers of overpopulation. And in your opinion, would you say that had we heeded his warnings at the time, we would not be in the situation we're in today with the carbon dioxide?
I'm sure we'd be in a situation, but probably we'd be delayed. That was in Ehrlich was about 1970. Yeah. He was an advocate of zero population growth. The ZPG was a big thing for a while. There was a guy just before him called Garrett Hardin, who wrote The Tragedy of the Commons. And this is a prime example of it. The example he used was a small field in England where all the farmers were allowed to graze their cattle on the commons. And it's great if you got 1 or 2 or 3 head of cattle and you got a lot of acres, it works well. But if you got 5 acres and you got 100 cattle, who gets to use the commons gets destroyed, right? And this is the same thing. The ocean, the air, the commons, and nobody controls it, nobody owns it. And so everybody uses it and dumps into it. And that is the tragedy of the commons. I'd highly recommend both books if anybody's interested.
So Bob, what organizations are really kind of on the leading edge of this? You mentioned like MIT, which is not surprising, but what other
Well, they're the scientists. They're not pushing so much the social aspect and the ethical side of things. I think there's a website, Oxford University has a website that they've done a lot of the academic studying of these different effects and how do you try to ameliorate some of the legal and the ethical issues. But the United Nations has the protocol, the London Protocol, or the one that just finished in Dubai, the COP 28. That COP is the Compact or Coalition of Partners. I forget what it stands for. It was part of the United Nations, and so they're the ones that are, basically in charge, if you will. But again, they have no regulatory power. It's up to each individual country. And again, who decides? You know, we have the space technology. Bangladesh certainly doesn't. They're not going to put up, you know, space mirror or stratospheric balloons or anything, but they're the ones that, you know, they've got 100 million people living right on the delta that get washed away every hurricane that comes in. The Seychelles got about 1.5 feet left before their island is covered. What rights do they have? What rights or what ethical stance should we take with their positions? Yes, sir.
I think there was a case in a company out of California was doing a sulfur dioxide aerolization thing, and they launched some balloons down in Baja California and violated some kind of international treaty between Mexico and the US and got shut down. Is there anybody that's encouraging that type of research or
Yeah, that guy was basically put up his own funds, put up a balloon and started. I don't know if he actually got the sulfur dioxide made or if he got stopped before that. But basically, there was no law that said he couldn't do it. The Mexicans came up with a law that sort of applied, but you know, he could have gotten off with a good lawyer. The iron fertilization guy did it on his own dime. Basically, you go out and do whatever you want in the middle of the ocean, and nobody's going to haul you in unless you're overfishing or something that's going to affect one of the big companies that's going to complain to their government. Nobody's going to really complain about something like a carbon capture plant. You put one of those up anywhere on the ground, everybody's going to say, yeah, that's fine. But if you're trying to put up a sulfur aerosol that could potentially affect US citizens, if no one else, I'm sure the US government would come in and step on you. Yes, sir.
Well, there was a splash on TV earlier this year about a university professor and his graduate student who'd come up with a highly reflective white paint that they were going to put on all buildings, rooftops, et cetera, but did you say earlier that's not?
Yeah, it's a good idea.
Effective?
It will help. And in fact, I did have a slide that I didn't put in, but you know, in terms of effectiveness for the global position, it's not real high up there. But for local, yes, if you had painted the streets down in La Cruces in Mexico white, instead of 140 degrees C at the ground level, it would be 90 degrees C or 90 degrees F. Just because you've stopped that heat absorption from the black asphalt. So every rooftop, you know, all you see, all your Walmarts and Targets and everything, all the new stuff is white because they can't afford to pay for the air conditioning over the groceries. If all the houses, you know, 10 million houses, whatever we have here in the States, if all the asphalt highways were painted white, it would help. But it won't solve you know, it's certainly not the legacy issues of the last 300 years.
that would be a good place to use the lime would be to whitewash all that stuff, huh?
There you go. Yeah. Now, remember, with the reflection and the solar radiation management, that does nothing at all for the CO2 levels in the air. And if you've got your space telescope up there, or if you're all your balloons pop and your space telescope gets hit by a meteor, what happens? Because now all of a sudden you've got the full sunshine coming down, but your CO2 level, instead of being 420 part per million, is up at 600. Global warming is going to go nuts. It's going to spike right up there. And who knows what other effects, you know, unintended effects that would cause. So you have to do it in combination.
The other thing I didn't hear you mention, you may have, was the carbon dioxide capture. I imagine it takes a lot of compressors and equipment to do that. Right. So and the same with the electrophoresis of the ocean water. All that has to be done with sustainable energy, right?
Exactly. All of these things cost money.
Yeah.
A lot of them cost a lot of energy. Where do you get that energy from? The first carbon capture plant was using natural gas to heat the amine solution up. And so it had to be oversized to account for the carbon dioxide produced by burning the natural gas to heat up the stuff so they could pull off the carbon dioxide. So yes, all of these things have a lot of negatives, but I didn't go into a lot of them. Again, the cloud albedo, putting the clouds up to cool down the Great Barrier Reef. Great idea, but you need a fleet of drones covering the whole ocean, and they'd have to be running 24/7. Where do they get the power? What is all that extra moisture in the atmosphere going to do, especially in the tropics?
Probably create a hurricane or something.
This is the satellite photo about 5 years ago, something like that. 2003, so 20 years ago, the Straits of Gibraltar, and these are all tracks of the ships as they pass through. And all these clouds come from the exhaust stacks on the ships because they were burning bunker C fuel, which is 4% sulfur. So they're making their own clouds, right? So cooling down the Straits of Gibraltar. What a great idea, except we've regulated that the ships, the International Marine Organization says, no more sulfur in the fuel. So they're burning diesel fuel now. So this, if you took the same picture again, you'd see pretty ocean and no cooling effect. So there's all these balances. Do you burn more here to capture more there?
You also got a kind of a paradox too, like you said, with the particulates turning the ice a darker color. The particulates could provide shade as well, but you know,
Not at ground level. Yeah, that's the thing. The sulfur particulates at 60,000 feet, if they stay there and there's enough of them, that'll give us the 1.5 or 2% reduction that we need. Down below, any dust or any particles are bad, just for humans, let alone the ice. The Swiss came up with a brilliant idea, but I don't know how good it is. They didn't like their glaciers starting to melt so fast. They didn't like the spotty color from the particulates, so they wrapped them in white plastic. Keeps the glaciers a little bit longer, but sooner or later they're going to melt.
They wrapped them all in white plastic.
Not all. Some of them are going to say. Now, where do you get the plastic from? Oh, comes out of an oil refinery.
In our paleontology class, Bob, we've been studying, back 150 million years ago in the Triassic, and we had mass extinction events, and a lot of those were caused by either asteroids hitting the Earth or acidification of the ocean and volcanoes. So in past history, we can see some major events that caused what we're seeing now.
Yeah, I don't know, you probably know better than I do, Dave, but the 65 billion year ago asteroid strike wiped out the dinosaurs. That was a big thing. Nobody had that idea 30, 40 years ago, whenever, forgotten his name. The guy that figured out the iridium layer in the clay around the Earth. So all of a sudden the attention kind of died from why did the dinosaurs die out? Well, it was this asteroid that killed them. Well, just so happens that about 100 million years before that, right? Or 50 million years before that, you had the Deccan Traps being formed, the big volcano split in India. And they put thousands of square miles of lava out and spread out over the place. And of course, when you got 1,000 square miles of lava, you got an awful lot of sulfur dioxide and carbon dioxide. So obviously the dinosaurs were struggling even before the asteroid hit.
Just a naive question about the trends. So having looked at climate change and geoengineering and the pace of acceptance that yes, it's human caused, and yes, these are real measurable changes happening to the planet. I don't get the same sense reading the news, whatever, that geoengineering strategies have taken hold or have traction yet. But do you have a sense that they do, that people are really considering?
In the science community, yes. In the general public, I don't think so. The IPCC, the Intergovernmental Pollution Control, whatever it was, every 5 years they come out with a report. They're starting to push it. This COP28 reaffirmed the targets of the 1.5 degrees or whatever, but came up with nothing conclusive this time. So I do seriously doubt that we'll see any government actions in the next couple of years. Unless you call up Barrasso and Hageman and Loomis and say, what can we do? Yeah. We start harassing them, maybe they'll try to put something together.
Well, Thank
All right.
Bob very much. Appreciate it.